Hello students, let us discuss more about the origin of spectral lines. So as we have seen, a spectral line is obtained when there is a transition of electron from one orbit to another, that is from higher orbit to a lower energy, which means an outer orbit to an inner orbit, and the amount of energy radiated h into frequency will be equivalent to the difference between the energies. So Bohr has already proposed what is the energy associated with an electron in an orbit n. So let us consider En to be the energy of the electron in the outer orbit and En to be the energy of the electron in the inner orbit n1. And the expression for energy is given by Bohr as En2 equals minus 1 by 8 epsilon 0 square z square e raised to 4 m divided by n2 square h square. Similarly, associated with n1 is minus, same thing, only difference is that instead of n2 you have n1 square. So the difference between these two energy will be emitted out as h into frequency. So from which we can calculate what will be the frequency of the emitted radiation, which is given by nu is equal to difference in energy divided by h from here. So this is equal to minus 1 by 8 epsilon 0 square z square e raised to 4 m by h square into the difference from En2 is 1 by n2 square minus from here is 1 by n1 square whole divided by h. Now taking the negative sign inside, we'll get it as 1 by n1 square minus 1 by n2 square. Now if you we also know that the velocity of light in vacuum c is equal to is related to the frequency as by the equation c is equal to nu into lambda, where nu is equal to c by lambda. So substituting these, we'll get it as nu is equal to z square e raised to 4 m 1 divided by n1 square minus 1 by n2 square by 8 epsilon 0 h cube can be equated to c by lambda, from which you can write 1 by lambda as taking c to the denominator as so and so, and 1 by lambda is denoted as wave number nu bar. So finally we have an expression which gives the frequency of emitted radiation if an electron transit from n2 orbit to n1 orbit. Okay, this was the interpretation given by Bohr based on his theory of atomic model. Now let us see whether it matches with experimental data of a hydrogen spectrum. For that, let us consider an hydrogen atom, and we know the hydrogen as atomic number 1. What does that mean? It has one electron revolving around the nucleus. So it is the simplest atom in the periodic table, and so this is the ground state of the hydrogen, and whenever the hydrogen is excited, that is whenever this electron is excited, a spectrum will be produced once it relaxes down to the ground state. So it is the simplest line spectrum one can obtain, and the spectrum obtained in spectral lines obtained in hydrogen spectrum is grouped into several series, and you know it, which are Lyman series, which comes in the ultraviolet region. Then you have Balmer series, which comes in the visible light region. Then Paschen series, which comes in the infrared region, and Brackett series, which comes in the far infrared region. So Rydberg has formulated a formula for the wavelength based on the experimental observation, and hence this formula is called empirical formula. And the formula was like this: 1 by lambda will be equal to some constant r into 1 divided by m square minus 1 by n square, where this m and n are some integers which has been devised in tune with the experimental data. and R is found to be called a Rydberg's constant, which is equal to 1.097 into 10 raised to 7 per meter. And it is also seen that M is less than N, and for any given series, for example Lyman, M will be constant while N will be varying one. Therefore, for a Lyman series, the value of M will be 1 and N is equal to 2, 3 and 4. So this was proposed by Rydberg based on the experimental details of a hydrogen spectrum. Now let's see whether the Bohr has successfully obtained this spectrum. So according to the Bohr, the spectrum obtained, the spectral line is given by nu bar is equal to z square e raised to 4 m divided by 8 epsilon 0 square c h cube into 1 by n1 square minus 1 by n2 square. Now for a hydrogen atom, you can substitute z is equal to 1, so you'll get a constant like this. So substituting the values for all these constant, it is found that the value obtained is same as that for a Rydberg constant. So which means that the Bohr has successfully explained what is given by Rydberg empirical formula. Now he explained each series in the hydrogen spectrum, and Lyman series was explained as a radiation emitter when an electron jumps from a higher orbit like second, third, etc. to the first orbit. So it becomes 1 by 1 square minus 1 by n2 square. So all the transition from higher orbit to the first orbit will be taken as Lyman, and it happens in ultraviolet. Similarly, Balmer series is obtained when a radiation is emitted when an electron jumps from higher orbit to the second orbit. So it becomes 1 by 2 square minus 1 by n2 square, where n2 can be any of the higher orbit than 2. It happens in visible light, and these 4 of them are said to be prominent ones because these transitions are happening in visible light. So these are the first set of wavelength which were observable at first because they are obtained in the visible light. Okay, so 3 to 2 is taken as H alpha, 4 to 2 transition is taken as H beta, 5 to 2 as delta, and so on. So the Paschen series is the next one, which is the spectral lines emitted when an electron jumps from higher orbit to a third orbit. So it will be given by 1 by 3 square minus 1 by n2 square. It happens in infrared region. And the bracket series for all the higher orbit transition to the fourth orbit. And there is a correction to the fun series. It is actually the fifth orbit transition to the fifth orbit. Okay, so which happens in far infrared region. So this is how Bohr explained the hydrogen spectrum. So in the orbital diagram representation, you can see that all the transition to n equals 1 is Lyman, all the transitions to n equal to 2 is Balmer, all the higher level transition to n equal to 3 are Paschen, all the transition to n equal to 4 are bracket series, and all the transition from higher orbit to n equal to 5 are fun series. And this could also be expressed in terms of energy level diagram. Earlier we have shown it using the concept of orbits. Now you are going to show in terms of the energy of each orbit. So Bohr has already given an expression for energy of each orbit as En is equal to minus 1 by 8 epsilon 0 square Z square e raised to 4 m by n square h square. For hydrogen, Z is equal to 1. So this expression would be like this. And for substituting all the constant, the only variable will be 1 by n square. So we will get it as minus 13.6 by n square in electron volt. So for n is equal to 1, the first orbit, the expression for energy will be minus 13.6 electron volt. For n equal to 2, it would be minus 13.6 divided by 2 square, and so on. And what is the other inferences you can make from here? That is the difference between the second orbit and the first orbit is almost like 10.2 electron volts, while the difference in energy between third orbit and the second orbit is like 1.9. So here it was 10.2 has come reduced to 1.9. So as we go higher and higher with the increase in n, the energy levels are getting closer. And what is the other inference? What about the value of energy of each orbit? The magnitude is actually decreasing, right? But due to the presence of negative sign, the value as such will be increasing. So as n increases, the value of energy will also increase. So there is a correction to be made. So the points to be considered is that ground state value is minus 13.6 electron volt, and as n increases, the value of energy will also increases, and the distance, the spacing between the energy levels decreases with increase in energy. That means the lines will get crowded together, and hence it will form a continuum of energy for very high value of orbits. Okay. So the two concepts to be considered in this transition is that the wavelength limit of transition, short wavelength and long wavelength. That is, here I have shown the transition of transition in a Bohr series. So here you can see from 3 to 2, the transition corresponds to red wavelength 656, and from 4 to 3, the transition corresponds to 486. Still lesser wavelength, and for 5 to 2 the transition occurs in blue wavelength, which is again at a lesser wavelength, and for 6 to 2 the transition is at the least among these four. So what does that indicate? As the energy difference between two orbits are more, the wavelength emitted will be less. Why that so? It is due to the relation of energy. Energy is expressed as h nu, which is equal to h into c by lambda, which means energy is inversely proportional to the wavelength. So the amount of difference in energy, if it is higher, will get shorter wavelength. Okay, the amount is higher, shorter wavelength. If the amount of energy is smaller, then higher wavelength. So for any transition, any series, there will be a shorter wavelength limit and a longer wavelength limit. Shorter wavelength limit corresponds to a transition from high energy, which is the highest energy possible, n equal to infinity to the n1 of that corresponding series. And what will be the longest wavelength? Longest wavelength corresponds to the immediate transition in the series. That means for Lyman series, it would be from 2 to 1. For Bohr series, it would be from 3 to 2, and so on. So this is a list of short wavelength and long wavelength limit for each series have been tabulated here. Here you can see any series will be called Lyman if the transition is to first orbit. So the short wavelength in the first to the transition will be from infinity to 1. Similarly for Bohr, the transitions to second orbit will be called as Bohr. So the shortest wavelength limit is from infinity transition to the second orbit. Similarly for Passion, infinity to third orbit, bracket infinity to fourth orbit, Fund infinity to fifth orbit. Similarly you have for long wavelength limit, the immediate transition to the Lyman series, that is 2 to 1, then Balmer 3 to 2, 4 to 3, 5 to 4 for bracket, 6 to 5 for fat. So these are very important based on this numerical problems will be asked. So hope you have understood Bohr atomic model. So thank you.